It's gonna start it. So good morning, everybody. So today is gonna be presenting to us Dr. Ryan Russell. So I'm gonna be introducing him. Thank you so much for accepting the invitation. Dr. Russell received his bachelor degree from Marquette University and his doctorate from Louisiana State University, where he studied cardiometabolic disease in the Department of Kinesiology. He has since completed postdoctoral fellowships at the University of Maryland School of Medicine, the University of California, Los Angeles, and at the Manzing Institute for Medical Research. He joined the Health and Human Performance faculty at UTRGV as an assistant professor in the fall of 2016, and he's currently carrying out studies aimed at the identification of specific pathophysiologies contributing to health disparity in populations at high risk for cardiometabolic disease. So he's going to be presenting to us the triaxial gut-liver-muscle relationship of cardiometabolic disease. The floor is yours.
Okay, let's see if I can remember how to share.
Yes, I hope so.
All right, did it work? Okay, so that's the talk, the triaxial gut-liver-muscle relationship of cardiometabolic disease. It sounded like a fun title, so that's what I went with. Hopefully it's going to be a fun talk. And I can't change slides. Oh, now I can. All right, so brief background. Type 2 diabetes, it's a big problem. If you exclude COVID, it's the fastest growing epidemic in the world, or pandemic, really. So the most prolific cause and consequence of diabetes is going to be, well, of insulin resistance, is going to be overnutrition. So without insulin resistance, there's no diabetes. And overnutrition, you could call it positive energy balance, which is just basically your energy intake exceeds the energy expended on a daily basis. So you gain weight. So diabetes and insulin resistance are characterized by hyperglycemia. Well, before I continue, can everybody hear me clearly? Because there's some times where my microphone...
Yes.
Okay, the wrong microphone is chosen, okay. All right, so hyperglycemia, so high blood glucose. Type 2 diabetes and cardiovascular disease are related to each other on a cellular and molecular level, and they have an effect of exacerbating each other or improving. So if you treat one, the other one gets better, or if one gets worse, the other gets worse. So to be clear, I study diabetes and its cardiovascular complications. Not like those other people that study cardiovascular disease and the metabolic complications. Completely different, exactly the same. But that's my perspective is diabetes and its related vascular complications. So from a physiological perspective, it's been reported as much as 80% of postprandial blood glucose is disposed of inside skeletal muscle. I mean, this is contradictory based on which articles you're reading, if it's a mixed meal or if it's a glucose drink. So that's the topic for another talk entirely. But briefly, if you have a mixed composition meal like a regular meal, most of the glucose is disposed of in the skeletal muscle. So we see problems in diabetes both with metabolism and with vascular function. So in metabolism, that's the traditional thought for diabetes and insulin resistance is that there's a problem within the myocyte, within the muscle, and there's impaired GLUT4 translocation. So you can't move the glucose into the muscle. And then the other school of thought is that it's really a vascular disease. So you have a problem with macrovascular and microvascular function, which limits the delivery of glucose and insulin to the skeletal muscle. So we're going to kind of look at both of those. So this is my wonderful little cartoon of a capillary. When I was in Australia, it was a capillary, not a capillary, and a myocyte. So what happens in a healthy system is the capillary carries the oxygen, insulin, glucose, etc., to the muscle. The insulin will bind to the insulin receptor and phosphorylate it, and the whole cascade of events happens before GLUT4 moves from within the myocyte to the wall, and it can grab glucose and transport it in. But when you have muscle insulin resistance, you have an impairment of the insulin receptors. There's less active insulin receptors. And so that cascade doesn't happen nearly as effectively. GLUT4 doesn't go to the outside of the wall, and it's not going to transport glucose in. So that's the traditional school of thought for insulin resistance. So let's start off with some metabolic impairment. One of the first things I did in grad school was a very simple study just looking at metabolic flexibility and to see if I could use that to detect early metabolic problems. So if you don't know what metabolic flexibility is, that's okay. I didn't know what it was when I did this study either. But in a nutshell, it's the ability to switch substrate oxidation upon stimulation. So to give you just a brief idea, when you're fasting, your body burns mostly fat. And you can measure this with indirect calorimetry, just the air you expire, and the value would be around 0.7. When you switch and you eat a meal, your body recognizes the spike in insulin and that you're in a state of a lot more nutrients. So you switch to burning carbohydrates and that whole body RER goes up closer to 1 because you're burning carbohydrates. The degree to which you switch, or how fast or how effectively you switch, is metabolic flexibility. So it's really like the sum of the change in RER over time. So if you're flexible, you switch from burning fat to carbohydrates pretty quickly, pretty robustly. If you're metabolically inflexible, you don't really switch that much. So this is kind of an important topic because it's been shown that people with diabetes are metabolically inflexible. Insulin resistance, you're metabolically inflexible, and obesity as well. So we're going to get into this a little bit more in a second. But first, I'm going to give you a brief outline of what we know about diabetes. You get diagnosed at one point, but you've probably had diabetes for years before your diagnosis. And before you even have diabetes, you could have what they call impaired glucose tolerant, or IGT. And it's basically the same as diabetes, except whenever you eat a meal or drink a glucose drink, the blood glucose doesn't get quite as high. You haven't hit that cutoff to call it diabetes. Doesn't mean that you're healthy. Before your blood glucose shows any signs of being impaired, you have insulin resistance. Now, people never know they have insulin resistance because your body just makes more insulin to overcome the resistance you have to insulin. So you make more and your glucose is normal. Doesn't mean that you're healthy. You're not. But this study that I did in grad school, it aimed to see if metabolic flexibility is in fact impaired in people before overt insulin resistance. So for this, I looked at people with a family history of diabetes. Now, a lot of people are starting to use this kind of population to study early insulin resistance because offspring of those with diabetes have about a 40% higher chance of developing diabetes than people with no family history, or FH minus. There hasn't been any kind of single gene or even gene cluster to fully explain this phenomenon of metabolic flexibility or even the likelihood of developing diabetes. However, there's been some really elegant work by Muyo and Holver and others showing that impaired fat transport as well as mitochondrial efficiency plays a big role in metabolic flexibility, at least in an animal model. So we've also seen a study from Leonie Hilbron that people with a family history of diabetes and insulin resistance at the same time are less metabolically flexible than an insulin resistance matched FH minus population. So that was the earliest that we've seen metabolic flexibility impairments. So how early can we really detect this? Well, it takes us to a study that I did in grad school, followed immediately by more studies. So this was very simple. I had healthy FH plus and minus. These were college students, actually even more than that. Most of them were college athletes, and the ones that weren't college athletes were very physically active, and some of them were even the trainers employed by the university to work with the athletes. So very fit, very healthy people. And there's virtually no difference between these groups, the FH plus and the FH minus. But I also had a type 2 diabetes group just so I could have a point of reference as a negative disease control group. And of course, they're going to be older and they're going to weigh more. So that's to be expected. So not to get into too much detail with this, because it was a very simple study, We found the obvious that blood glucose is impaired in people with diabetes, so that's not much of a surprise. And the healthy groups, very active. There's no problem at all with their postprandial glucose levels. However, when you look at the delta RER, which is the measurement of metabolic flexibility, we see that the only group that was flexible was the one with no family history of diabetes. The FH plus group, even though they were physically active and young, they were just as metabolically inflexible as people with clinically diagnosed type 2 diabetes. So this was a really exciting finding for me because this has never been shown before. And I kind of call this the little paper that could, because even though it's a simple study, it really developed a lot of initial of subsequent questions. So that's why I like to start with this study in a presentation, because without this study, I wouldn't have had any of the rest of the data, which let's get into. All right, so we talked about the timeline of diabetes and impaired metabolic flexibility, but I had a conversation with a scientist in Australia one day. And so it led to a talk that she gave at UCLA when I was there. And her work is on microvascular blood flow. Specifically, it's the recruitment of blood flow in the capillaries of skeletal muscle. It took me a while to realize that, because she's from Australia and I didn't know what a skeletal muscle was. So the capillary flow in skeletal muscle. So I had this idea that my work in grad school with metabolic flexibility and her work with the microvascular blood flow were probably connected. And this conversation led to a couple of small grants and my third postdoc. So the rationale behind this is, again, the same little cartoon, except this time, instead of the muscle being the model of insulin resistance, it's the vascular system. So what happens with the vascular system is you have, if it's resistant to insulin, it's not going to dilate appropriately. And in fact, it will actually constrict. And that's going to reduce blood flow to the capillaries, which will reduce the delivery of glucose, insulin, and oxygen, etc., hormones, everything to the myocyte. So if you're not delivering the glucose and the insulin as effectively, then it's obviously not getting in the muscle cell. So this can compound the problem with diabetes. So a little anatomy lesson here. We have a conduit artery, which is key for compliance. Then you have resistance arterioles, which help regulate total flow to any particular section of the body. Then you have your smaller precapillary arterioles, which still have smooth muscle, and they can react to nitric oxide, expand and contract, and they regulate the capillary perfusion, or how much blood goes through the microvascular system at any given time. And then, of course, the capillaries, and that's the site for substrate exchange and delivery of insulin and nutrients, etc. So we mentioned total flow. So we focus more here on the precapillary arterioles and the capillaries themselves. So what we know is that insulin can regulate the microvascular blood flow, or the responsiveness to any stimulation like a meal within the skeletal muscle, and that the microvascular recruitment has actually been shown to happen completely independent of changes to total blood flow. So you can have an increase in blood flow to that limb and no change in microvascular, or a change in microvascular. Or you can have no change in total blood flow and a robust increase in the microvascular blood flow within a capillary bed in a skeletal muscle. So they seem to be relatively independent. So how this works, I actually had a different, more complicated slide, but so here is a picture of the precapillary arteriole where insulin is going to bind to the receptor, and ideally it binds, there's a cascade of events that happen, and ultimately you stimulate nitric oxide production. Nitric oxide is a very potent vasodilator. It's also got a very short half-life. So when it's secreted, it acts locally and it causes a dilation of those arteries or arterioles. But at the same time, your body also has a very similar signaling cascade with the insulin receptor, et cetera, except instead of nitric oxide being the end product, it's endothelin-1. And endothelin-1 is a very potent vasoconstrictor. And in a healthy system, these are in a homeostatic balance. And in an unhealthy system, the endothelin-1 kind of outweighs the nitric oxide, and you have vasoconstriction and a reduction in blood flow and subsequent hypertension, etc. Now, the interesting study that she was doing used microbubbles to look at blood flow within skeletal muscle. And those of you that have seen me present before, go ahead and nod off for a couple minutes. This is the same movie. You can't see blood with an ultrasound. So it doesn't make any noise going through capillaries because it's very passive. So we infuse these microbubbles into circulation because we can see the microbubbles, and we can record a movie showing the timeline of how long it takes for them to show up, the total saturation. You can see in the top left corner, you're starting to see a little bit of white twinkling, and those are the microbubbles entering circulation. The yellow box is a small artery or an arteriole right there within the muscle bed. So it's starting to become kind of saturated with those microbubbles. The image on the right is without the contrast enhancement. So you can't really see much. You can see the artery is doing something, but you can't see the blood flow. Now within that kind of drawn region of interest in red, that's the skeletal muscle with the capillaries carrying all of these microbubbles. So here you can see the saturation of microbubbles, which is going to be what we call the saturation of blood. And then we can actually send a high frequency pulse to rupture these microbubbles while we're recording the movie and measure how long it takes for them to reach a steady state again. And that's a measurement of velocity. So if we take the velocity and multiply it by the total saturation, we get the total blood flow within the microvascular system at any time. So that's kind of what the technology we're using for these studies. I will say it is considered the gold standard for microvascular blood flow. So this is one of the studies we did in Australia, and it really did come from that little study that could back from LSU. We wanted to kind of repeat the same study. We did it with a glucose drink and a mixed meal, but for this particular paper that I'm showing, it's under review right now, we deleted the glucose drink. We're just showing the mixed meal because the results are actually a little better. So the FH plus and minus groups, they're pretty much the same for metabolic function. The HbA1c, which is an average of your blood glucose over 3 months, it's exactly the same. The blood glucose changes are basically the same, except at 90 minutes we do see a statistical difference, and then they come together again. And I do want to point out that the microvascular measurements we do are fasting, and then again 60 minutes after they drink this mixed meal. So the insulin levels at 60 minutes are the same between groups, so we don't think that insulin levels are causing any potential differences. Again, insulin doesn't change at all. The glucose is slightly different, insulin's the same. But then if you look at D, that's the microvascular blood flow, the perfusion. You can see in the FH minus group, there's a robust increase in blood flow within the capillary bed of skeletal muscle. And in the matched FH plus, you don't see that at all. It's just completely absent. Well, let's also look at the metabolic aspect. We looked at the RER over time, and that's can be used to calculate substrate oxidation. And then the bottom F, that's the graph for metabolic flexibility. So it did reproduce the same results we saw before. FH minus, very flexible, FH plus, very inflexible. So it does appear that there's a strong relationship between metabolic flexibility and microvascular perfusion, although we didn't establish a statistical relationship, so there's probably some other factor involved. We also included people with diabetes in this study. So when you look at the blood glucose, obviously people with diabetes have impaired glycemic regulation in A, and then B is the area under the curve. So it's very clear, the healthy groups are healthy, the diabetic group is not healthy. The insulins are actually pretty much the same between all three groups, both at each time point and the area under the curve. And the RER and metabolic flexibility supports our previous findings that FH minus are metabolically flexible and FH plus are metabolically inflexible. We had our fingers crossed for this paper. It's under review. So a little bit deeper into the microvascular function, I mentioned the different ways that we look at it. There is skeletal muscle microvascular blood volume, and that's the total saturation within the muscle. It's higher, substantially higher in the FH minus group. It does appear to go up some in the FH plus group, and then nothing happens with diabetics. But then you look at beta, which is a measure of the velocity. And I mean, if you're going to squint, you could say, well, maybe it's going up a little in the FH minus and maybe going down a little in the FH plus, but no real changes. but C is where the real money maker is. That's the total blood flow. When you multiply A times B, you get C. Big increase in blood flow to the capillary beds in the muscle of FH minus, and no change postprandially in FH plus. So if you recall before, I showed a slide talking about 80% of blood glucose disposal happens in the skeletal muscle after a meal. Well, that's not necessarily the case, is it? Because if there's no increase in blood flow to the skeletal muscle, then you're going to have a severe fluctuation in where it's being disposed of. Is it happening in the muscle the same in both groups? I can't imagine it is. I haven't done the study to prove it, but there's less being delivered, so there's probably less disposed of in the muscle. And since the blood glucose is the same across the different time points, that must mean there's another tissue, a metabolically active tissue that's being utilized. So some of the studies we're doing currently, we're still doing the microvascular, we're still looking at muscle, but I've also incorporated abdominal adipose tissue as well as liver to try and find out where is the change in blood flow happening to explain the lack of change of blood flow we see in skeletal muscle. I have nothing to present on that one yet. Just thought it was interesting and wanted to put it out there. And I can't change slides again. Okay. Macrovascular. So here you have the brachial artery diameter, and I use brachial artery here because the muscle bed we used for microvascular was the muscle in the forearm. So the brachial artery diameter increased postprandially in the FH minus group, but not in the others. The velocity was statistically unchanged among all three groups, but as many of you might know, if you increase the diameter of a tube that a liquid flows through, you can increase the total flow drastically. So that being said, total brachial artery flow did increase significantly postprandial in the FH minus group, with no changes noted with FH plus or those with diabetes. But there's more to it than just conduit arteries. There's also arterial elasticity, for example, and mean arterial blood pressure. Well, mean arterial blood pressure and pulse wave velocity were both the same in the healthy groups and both impaired in the diabetic group. But there was a reduction in forearm vascular resistance noted postprandially in the FH minus group, which could help explain the increase in blood flow to the capillary beds. And if at some point I'm getting quiet, just somebody let me know and I'll increase my volume again. It happens when I'm teaching class. I forget to project. So how is liver function related? This has all been about vascular and metabolic, but the title suggests that liver is going to play a role. So what does gastric permeability, circadian rhythms, and artificial light have in common? This sounds like the beginning of a very bad joke, but it's not a joke. They all adversely affect liver function related to insulin resistance and type 2 diabetes. So I'll show a little picture that kind of shows what the role that liver has in some of this. So obviously you eat food, it goes through your intestines and it's absorbed into the bloodstream. That's the normal process. But whenever you have a problem with there's a noise in my computer. When you have a problem with intestinal permeability, these tight junctions between the cells can either become less tight or more tight, and you can have things passing through the intestines that are not supposed to, which is one reason we see a difference in, say, LDL, as well as lipopolysaccharides. So these cholesterol particles are circulating around, HDL binds to them, carries it back to the liver through the SRB1 receptor, and it's broken down, hopefully, by the liver. But what happens a lot of times is you have an accumulation of fat in the liver, and it could lead to non-alcoholic fatty liver disease. So oftentimes with advanced diabetes, you also see liver disease. So we're going to look a little bit about the relationship of that. So this is a story about gastric permeability. So with gastric permeability, we looked at circulating zonulin in people with insulin resistance and type 2 diabetes. Now, others have shown that having type 2 diabetes or insulin resistance may increase the level of lipopolysaccharides that are absorbed from the intestines into the bloodstream. And these are bad to have, just to be very clear. Lipopolysaccharides are an antagonist against your health. So they're bad for the vascular system, they're bad for liver function. So you don't want an increase. But our data suggests that this relationship might go the other way around. It could be that the increased absorption of lipopolysaccharides might actually make it more likely to develop insulin resistance and type 2 diabetes. So this is a very busy slide that I don't expect anybody to really comb over in any fine detail, but it's clinical characteristics and some different biochemical parameters within the subjects in this study. And the subjects were NGT for normal glucose tolerance. So when they do a glucose drink, you see a normal change in glucose and it comes back down again. So you could think they're probably metabolically flexible. Then you have IGT, which is your impaired glucose tolerant, and then clinically diagnosed type 2 diabetes patients as well. So I just want to draw your attention to the bottom where we see serum zonulin levels. So there's a stepwise increase in serum zonulin from normal glucose tolerant to impaired glucose tolerant to type 2 diabetes. And so zonulin is a protein that actually regulates the permeability of the tight junctions between the cells inside the wall of the digestive tract. So when you have more zonulin, the junctions become less tight or your intestines become more leaky. So people say, oh, you've got leaky bowel syndrome or something. Well, that's really what they're talking about. Higher zonulin and particles that aren't supposed to pass through are now more readily able to pass through and get into circulation. So this is a correlation of serum zonulin with different measures that are typically measured in these diabetes studies. We see a strong statistical relationship between zonulin and waist-hip ratio, fasting plasma glucose, 2-hour plasma glucose, HbA1c, triglycerides, cholesterol, HDL, insulin resistance, and even certain markers of inflammation like TNF-alpha. Now, correlation doesn't mean causation, obviously, but it at least gives us a direction in which to look. So when we take it a step farther and we look at the kind of a multiple stepwise linear regression analysis, looking at different variables that are related with insulin resistance, we see zonulin is a big player here. You know, nobody goes out into science to say, all right, we're going to figure out how to stop zonulin. No, in my field, you don't really care too much about that. You want to figure out how to reverse insulin resistance. So that's why we're focused on that. And like it turns out, HDL, HbA1c, BMI, or body mass index, and zonulin are all independent risk factors for insulin resistance. So kind of sum it up, elevated zonulin in the serum in type 2 diabetes correlates with inflammatory markers and dyslipidemia. Zonulin is independently associated with insulin resistance and type 2 diabetes, which suggests a role perhaps in the pathophysiology or the onset of diabetes. The higher zonulin levels lead to an increased gastric permeability, higher serum lipopolysaccharides and cholesterol absorption, and then subsequent cardiometabolic disease. So this has implications for, well, at least the LPS and cholesterol passing through the intestines has implications for liver dysfunction and non-alcoholic fatty liver disease. So that being said, that brings us to another study where we look at the microbiome and liver function. And this is not in people this time, this is an animal study. In this study, there's four groups. 2 groups have different diet. There's normal chow diet, and then there's a high-fat diet. And within each of the diet groups, there is a difference in the exposure to light. So you have a light-dark cycle, so normal, 12 hours, and that's LD. And then you have what they call a light-light cycle, which is just 24 hours of light exposure, and that's the LL group. So here we see A is blood glucose levels, and there's a stepwise increase in blood glucose from the normal diet with the regular light-dark all the way up to the worst one, which is the high-fat diet and constant light exposure. And if you look at B, that's the area under the curve, shows a nice stepwise progression, or maybe not so nice if you're the live rats in the high-fat diet. And in C, we're looking at the insulin tolerance test, where you inject D-glucose, and then you measure insulin over a period of time. And the same kind of thing happens if you have a normal diet, you're better off. If you're exposed to light, constant light, you're worse off. And if you have the high fat diet and the constant light, you're in the worst group. So you're the most insulin resistant. Now, this is a bit of a complicated slide, so I just want to simplify it a little bit. Basically, this slide shows that the high fat diet, constant light group, it alters the makeup of the microbiome inside the rats, and it creates a specific or multiple specific microbiome clusters, which are genetically related to each other. And they may help explain the impaired glycemic regulation noted with the constant light exposure. So that's what these series of graphs actually say. So the light exposure alters the microbiome. The alterations seem to be clustered in a genetically related fashion, and there's a statistical relationship between these altered microbiome and the impaired metabolic function. So here we say that the constant light exposure has the impaired gut barrier function and the gut-liver axis in the high-fat rats. So in A, you see the serum lipopolysaccharide, which again, that's a bad particle you don't want, substantially higher in the high-fat LL group. And then in B, you have the LBP messenger RNA, or the hepatic lipopolysaccharide binding protein. So much higher in a constant light environment. So not only is this LPS getting absorbed more readily from the intestines into circulation, you also have a serious increase in the binding protein in the liver. So it's most likely finding its way into the liver, contributing to the non-alcoholic fatty liver disease. So this kind of sums up the study. Constant light exposure will exacerbate problems with the microbiome and liver function, but much more severely if it's combined with a high-fat diet. So the high-fat diet, constant light exposure, degrades the gut barrier function, leads to increased lipopolysaccharide translocation into the bloodstream, and also uptake into the liver. Which I think is a nice segue to go to the next study, which is the effects of constant light exposure on sphingolipids, or sphingolipidomics, and the progression of NASH in high-fat rats, high-fat diet rats. So hepatic steatosis is basically fatty liver disease. So in A, we see that the high-fat diet plus the light rats, or the constant light, they have the most fatty livers. And in B, you look at the liver triglyceride levels. And again, when you have the high-fat diet and the constant light exposure, you have the highest liver triglyceride levels. See that they weigh the liver, and if you're on a high-fat diet, you have a higher weight in your liver. And in D, you look at the steatosis and inflammation scores. And so again, if you have a high-fat diet, your steatosis is higher, and if you combine that diet with light exposure, then your inflammatory scores are much higher. And then E, I find particularly interesting. So E, we're looking at serum alanine aminotransferase, or ALT, and aspartate aminotransferase, or AST. And what these do, these help convert, say, alanine or aspartate into glucose. So what we see here is with the high-fat diet and the constant light exposure, both ALT and AST are increased, which would suggest that we're going to have a problem with fasting blood glucose, because this is not in a fed state right here. So these amino acids are likely to be converted into glucose, although this study has not actually taken that step forward. And then in F, we see the qPCR of the liver circadian clock genes. In the high-fat diet, constant light group, they're not in line with the others. So we can see there's something wrong with the genes associated with circadian rhythms. I mean, that would make sense. If you have light on 24 hours a day, it's going to mess with your circadian rhythm. So here there's a heat map of lipid metabolites in the plasma in A And in B, it's a heat map of lipid metabolites in the liver. And both show kind of the same thing, is that there's an increase in sphingolipids for the high-fat diet, constant light exposure rats. And sphingolipids they're both inflammatory particles and also signaling molecules, and they're highly related to insulin resistance and type 2 diabetes. So ceramide comes to mind as one example of a sphingolipid. Well, can liver dysfunction causing insulin resistance and type 2 diabetes be reversed? Well, this is a much more recent article looking at liver alanine catabolism and how it promotes skeletal muscle atrophy and hyperglycemia in both people and rodents with type 2 diabetes. So for this, alanine, it's considered the major or the primary amino acid involved in gluconeogenesis. So gluconeogenesis is the conversion of a substance back into glucose in the liver. So in this case, the substance would be alanine. So it exists in pretty low quantities in people with type 2 diabetes compared to a control group. And the diabetics actually have higher blood glucose excursions, obviously because they have diabetes, likely due to the increased alanine glycolyl transaminase isoforms. So I like to just call it GPT because I don't like to say those words in front of people. So here you look at A, it's the serum alanine. It shows a big increase in serum alanine in a wild type rat versus the DBDB rat, which is engineered to develop diabetes. And at the same time in B, you look at the glucose, and glucose, it flips entirely. So with the DBDB rats, glucose goes way up, and in the control wild type, it stays down. And this is with an IP injection or an interperitoneal injection. And then C, you'll get liver messenger RNA expression of transcripts that carry the GPT, which, by the way, is also known as ALT from the last study, the alanine aminotransferase. So GTP here is the same as ALT from the last study, which is why I think it's interesting. So that's much higher, much higher. Let's see, D, liver protein expression for ALT isoforms in the wild type versus the DBDB. And you can see the staining is much more robust with the DBDB mice. And you can see the graphs as well, illustrating the change. The ALT is much higher in the DBDB mice. So there's a much higher conversion or much more efficient conversion of these amino acids into glucose. And then you see the ALT immunohistochemical staining. And F, I find also quite interesting. That's the GTP or ALT activity in the various mouse models of obesity and how it's related to blood glucose. So higher liver GTP or ALT activity is also related to higher blood glucose. And when you look at humans, so the next couple are looking at humans, we have normal glucose tolerant group versus a type 2 diabetes group. And the plasma alanine goes up in the normal glucose tolerant with a meal, where with the diabetic, it just stays the same. And then in H, you look completely different, the liver messenger RNA for ALT or GTP, which is the same thing here, much higher in diabetics. So there does seem to be a driving force with the conversion of alanine into glucose for people with diabetes. Now, there's a lot of graphs here to show the same overall message, that silencing both, but not individual, liver alanine aminotransferase isoforms affects the systemic alanine and glucose homeostasis upon diverse nutritional challenges. So this illustrates that these transferases are in fact responsible for the change in blood glucose. When you inhibit these transferases, either through a chemical inhibitor or a knockout gene, then we see normal glucose tolerance is restored, at least in the rats. And then also silencing both the liver alanine aminotransferase isoforms retards the hyperglycemia in mouse models of obesity and type 2 diabetes. So a lot of redundant studies just to kind of prove the point that alanine metabolism is a very significant driver of both fasting and postprandial blood glucose in the state of disease. And further, if you disrupt the heightened liver alanine catabolism, we also see improved skeletal muscle size and function in the mouse models of type 2 diabetes. So this is kind of an interesting finding, I think. What this basically means is if you are converting alanine to glucose, it's somehow causing a problem with the size of your muscles. They are smaller, you have atrophy. And if you can stop that conversion of alanine into glucose, you see an increase in skeletal muscle size. And these are in rodents that are kept in the same conditions. They're not in the gym lifting weights or anything. Although I would love to see a video of a mouse or a rat lifting weights. That would be really funny. So altered alanine metabolism contributes to hyperglycemia, both fasting and postprandially. It contributes to sarcopenia, thus decreasing the metabolic disposal area for glucose. Since we know that postprandially about 80% of glucose is disposed of in the muscle, this problem with alanine is compounded. You're converting it to glucose and you're reducing the size of the sink where the glucose will be disposed. You reduce the alanine metabolism, you also reduce blood glucose, and you promote muscle growth. This is all done both in cell culture and also knockdown experiments. But can the cardiometabolic pathophysiology be reversed in humans? So we want to determine if insulin resistance and impaired metabolic or microvascular blood flow can be reversed with resistance training. So why resistance training? Well, it's been shown to improve endothelial functions similar to aerobic training, which we've done aerobic studies for decades, and resistance training is kind of newer on the block. I'd say it really took hold about 15 years ago or so. It's been shown to reduce inflammation, improves insulin sensitivity. It can enlarge the area for glucose disposal, which would be the muscle, which could potentially lead to longer insulin sensitizing effects than aerobic exercise. Both are great for improving insulin sensitivity, but if you're doing aerobic, we found that you could be a runner and run every day for 10 years. But if you're predisposed to insulin resistance, you stop running, and 2 or 3 days later, you're suddenly showing all the signs of insulin resistance again. But at least with resistance training, if you're increasing the size of the muscle, in theory, it could take longer to reverse the positive effects of this exercise. Other things, I mean, you can reduce bone loss, and bone is actually a very important signaling entity for insulin sensitivity and insulin resistance. So again, that's a talk for another time. You improve strength and physical function, particularly with elderly, and you can utilize more total muscles in one session than aerobic. So potentially having a greater insulin sensitizing effect. And again, it was a plug to a paper I published back in the day. It reduces fasting blood glucose. Okay. So the design of this study are people come into the clinic and they get a DEXA body scan. So a dual energy X-ray absorption for bone density and body composition. And they're fasting, they do resting metabolic rate, and we do brachial artery measurements with the ultrasound, as well as contrast enhanced ultrasound. That's the microbubbles I spoke of. And blood draws at various times, including fasting. And after fasting, and all the fasting measurements are done, they do but for this one, it was a glucose test, not a mixed meal. So they drink the glucose, and then you put the metabolic hood back on, you measure the change in substrate oxidation for metabolic flexibility for 60 minutes. And then at 60 minutes, you reassess brachial artery function and microvascular function with a contrast enhanced ultrasound. So to get into this study, you had to be between 18 and 60, not obese, not have no history of microvascular complications. You could have controlled hypertension, but you had to be sedentary. Obviously, this is an exercise intervention, and you can't intervene with something people are already doing. Weight stable and non-smokers. So pre to post training, we see some changes in things, and obviously seeing a change with exercise, that's not interesting. So I actually highlighted the things that were not different, like weight and BMI. In 6 weeks, so many things improved. Body composition, fasting glucose, HbA1c, but I thought it was interesting that neither weight nor BMI changed at all in people. So all these changes occurred independent of changes in body weight. So going a little bit deeper, you look at pre to post resistance training. There's a big improvement in your insulin sensitivity. Total cholesterol is lower, triglycerides are lower, and of course, relative strength went way up. I put this in here just because I saw a resistance training study once when I was in grad school that showed that 2 or 3 months of resistance training had no positive health impact on women with X, Y, and Z. And I thought that was hard to believe. And I looked and there was no change in strength. So are you really training if there's no change in strength? No, you're not. So I have to put that in here just to show, yes, these people are being trained very hard, actually. So some vascular responses before and after training. We look at microvascular blood flow, and in people with diabetes, there's no difference between fasting blood flow and post-oral glucose challenge blood flow within the skeletal muscle. After 6 weeks of exercise training, there's a big increase in the insulin-stimulated microvascular blood flow. So I say insulin-stimulated because when you drink the glucose, insulin is increased in circulation, binds to the endothelial cells, causes vasodilation and increased perfusion in the capillary beds. If you look at capillary density, there have been studies that show that cycle training in elderly veterans, you see an increase in a lot of glycemic regulation, but also an increase in capillary density. Well, that's a 6-month study, and this is 6 weeks. So we didn't do biopsies, but what we did is a surrogate measure. We know that even a small muscle contraction stimulates 100% of blood flow within the capillaries of that muscle. So that's what we did. We compared baseline to post-muscle contraction blood flow as a surrogate measure of capillary density, and there was no changes at all between pre and post training, as you can see in D. So the changes we see are a change in blood flow, not a change in capillary density. And if you look at the brachial artery, before training, there's a big increase in brachial artery blood flow, and then after training, it is muted for some reason. You don't see the big increase in blood flow. We looked at microvascular flow in the skin with laser Doppler flow, and we saw no changes until around 60 minutes. But then the area under the curve, again, no changes. So a lot of people like to use laser Doppler flow as a measurement of muscle blood flow. And honestly, it just doesn't penetrate deep enough to get into muscle, especially when you're doing diabetic population because they have adipose tissue. So we use that to look at if it could be a surrogate measure, and it's not. It's measuring skin, and there's no change in the blood flow in the skin. So some of the metabolic responses. There is an improvement in blood glucose at every time point, fasting and every time point after the glucose challenge, and that's represented in B at the area under the curve. Insulin was not changed at all, so if insulin is the same and glucose is improved, it suggests that there's an improvement in insulin sensitivity. We also took a look at advanced glycation end products, and we did see that after training, there's a big decrease in advanced glycation end products, but we didn't find a relationship between that change or any of the other measures that we did. So looking at central and peripheral blood pressure changes, we actually didn't find any difference at all in the hemodynamics of these diabetics. Now, that's not to say that there weren't any changes. If I could go back in time and change the design of the study, I would, because what we did is we had them not take any of the diabetes medication for 2 days. But for some reason, we thought, all right, no problem, you can take your blood pressure medication. So under these testing conditions, they're regulated anyway. So maybe there's a change, maybe there's not. We can't really tell. Before and after training, there was no change in their diet. So we did questionnaires assessing what kind of foods they ate, and there was no change. So in summary, exercise is good for you. 6 weeks of resistance training improves microvascular blood flow, and glycemic regulation. And what we found is doing a stepwise linear regression analysis that 47% of the improvements we saw in glycemic regulation were actually caused by the increase in microvascular blood flow within a skeletal muscle. And that was really a very interesting finding for us. That's we all know exercise is good for you, and that's a boring message, all right? I don't care. Why is it good for you? Okay, we have an answer. Exercise stimulates a greater response in microvascular blood flow within the skeletal muscle, and that represents a 47% improvement of glycemic regulation. What the other 53% is, I'm curious. So if we also do the same kind of resistance training in healthy, unfit people, I'm going to go through this kind of briefly. We have FH plus and minus. They're all fairly healthy, and they went through the same, like I said, same training. We see some changes, nothing drastic. We do see non-esterified fatty acids tend to go down, or that's free fatty acids, and strength goes up. Again, fasting glucose goes down. Okay, well, the interesting part of this study to me is looking at the acylcarnitines. So in order for fat to be oxidized, it has to be attached to a carnitine group so it can pass through the mitochondria. And if it passes in, it can also leave. So there's an influx and an efflux. So we looked at the pattern of acylcarnitines between these groups before and after training. And although the degree of change wasn't different between groups, we did see that some of the differences in these acylcarnitines individually before and after training were different. So I guess a better way to say that is we saw a reduction in the disparity of lipid oxidation between the FH plus and FH minus groups as measured by plasma acylcarnitines. Taking a step farther, we already talked about how having a family history of diabetes predisposes you to getting diabetes. So it's bad. You don't want that, right? Okay, but acylcarnitines should be related to free fatty acids. That's a normal physiological response. And we see a correlation here between multiple acylcarnitines and the free fatty acids only in the FH plus group. So if having a family history is bad, why do we see a normal response to fat oxidation in this group and not the FH minus? It's an interesting thing. I'm not going to get into it right now, or maybe a little bit. Metabolic impairments in diabetes and FH plus are concurrent with impaired microvascular blood flow, but they don't appear to be directly related. There's some sort of an intermediary, and I think it has to do with acylcarnitines. Liver function is impaired with light pollution and a high-fat diet, contributing to insulin resistance, diabetes, and non-alcoholic fatty liver disease. Pathophysiological alanine metabolism in the liver contributes to hyperglycemia and sarcopenia, and resistance training increases lean muscle mass, improves glycemic regulation, and reduces disparities in lipid oxidation. And with that, I finished just barely in the nick of time. So I want to acknowledge the team of people that I worked with in my last postdoc, as well as other collaborators from different universities, collaborators in the past. And then I usually make a joke about this funding was brought to you by the letters NIH, ACSM, NIMHD, VTAHSP, RHH, ISRP, and NHMRC. And that brings us to the end of this very long presentation.
Thank you so much, Ryan. Nice talk. Now we're open for questions.
Hi, Ryan. This is Saris. Thank you for an excellent presentation. Can you hear me?
Yes, I hear just fine.
Okay, great. It was a lot of information, but really wonderful. So my first question was, does it matter which skeletal muscle you measure the microvascular blood flow? I mean, brachial versus thigh versus calf versus whatever.
Well, I can't say for every single muscle, but there's been studies that looked at calf, at quadriceps, and at forearm, and they show the same patterns. And in my lab here, I've actually measured both quadriceps and forearm, and I see the same pattern. I actually I don't want to say I'm going to switch to the quad, because I'd rather not measure total blood flow within the leg because that gets kind of personal. But it's a prettier picture. There's more muscle that's easier to see, and you have the same patterns.
Okay, great. And also, you mentioned various genes involved in improving microvascular blood flow. And I'm sure mitochondrial genes are involved as well. Is the literature out there showing that?
I'm not aware of any literature showing a genetic connection with microvascular blood flow, but there's some very good evidence to show different genes for fat transport. And one of the things that we've shown in my other diabetes group in Australia is that circulating lipids have a big impact on microvascular blood flow. So if you increase lipids, you're going to decrease the reactivity of the microvascular system. So genetic regulation, I would say, is indirect, at least at this point of our knowledge.
Okay, and for your gut permeability studies, where clock genes and circadian genes were looked at, I'm sure there's literature out there showing that melatonin is decreased and its effects on mitochondrial genes too.
Yeah, you actually mentioned a study that I was just thinking about doing last night. As a matter of fact, I was kind of thinking about this presentation, and my old advisor at LSU did a very small pilot study looking at melatonin dose on glucose tolerance and a couple of things. And yeah, I'm sure there is evidence. Since I actually just barely thought of this last night, I haven't looked it up, but it's something that I'm very interested in because, as we all know, light, especially artificial light, affects melatonin levels. And is it really as easy as, in today's society with all the light pollution we have and staying up late, is it really as easy as just taking a 5 milligram melatonin pill and boom, suddenly you've cured all of these problems? I'd be shocked, but I'd like to be the one who publishes the shocking data.
Well, thank you very much.
Do we have more questions? I don't
I
think so,
officially put them all to sleep.
Maybe they're sleepy.
I think so.
So, anyway, thank you so much, Brian. I appreciate it. Nice talk, and I hope you get a lot of collaborations.
Thank you. I'm open for suggestions, as it says.
For sure. I'll be here to measure all your ELISAs.
I'm looking forward to collecting a little bit more data so I can give you as much blood as I can.
Yes, for sure. First, we need access to a freezer, correct? Yes.
That's true. Yeah. Hey, I'm on campus. I might as well test it out.
Yes, please do. Thank you so much, everybody. I really appreciate it. So now we adjourn. Thank you,
Thank you.
Ryan.
Thank you. Bye.